Good morning. We continue our presentation on synthetic polymers. The second half focuses on structural properties and methodology for characterization of polymers. There are different methodologies that are used to characterize polymers. Basically, molecular structure of these materials determine their ultimate properties. Things like molecular weight distribution, crystalline structure, morphology, and others are structural properties that determine the ultimate properties of polymers. These properties includes mechanical properties, the strength, toughness, stiffness, electrical properties such as conductivity, optical properties like refractive index and light absorption, resistance to chemicals, light, corrosion, and thermal properties. These are all important characteristics in designing a particular polymer for specific application. Here is a schematic and a diagram that shows tensile strength testing. This is usually used for rubber-like materials as well as sheets and films, polymer films. Sample is stretched between two grips here, and the tensile strength is monitored, stress versus strain, and elongation is monitored here. And as finally, it is possible to basically determine at what point this sample breaks and falls apart. So it's a measure of brittleness, elasticity, and toughness of that particular polymer. As a result, it's possible to make a map like this that compares a specific polymer composite with other materials in terms of their stiffness and their strengths. We can compare carbon fibers with metals, glass fibers, and other fibers. Electron microscopy is extensively used when we want to study morphology of polymers. We can look at crystalline structure. Here is an example where incompatible polymer blends with and without a compatibilizing block copolymer is used here. Electron microscopy is also used to look at crystallization. In this particular case, is looking at polyethylene samples. We continue with some characterization methodologies that are used in coatings industry. These include molecular weight characterization of resins and latex that are used in different type of architectural and industrial coatings. Also methodology to look at the particle size of these resins and surface charge. These resins in terms of structurally falls into three categories. One are the latexes that are used in waterborne coatings. These are spherical particles and can have a very high molecular weight in the range of 500,000 to 1 million, and a particle size in the submicron range. Then we have the colloidal dispersions and water-soluble or water-reducible resins. that are lower molecular weight and can have different functional properties to impart surface charge and stability in aqueous systems. To study molecular weight and molecular weight distribution, and an instrument called high performance gel permeation chromatography is used, which is shown here schematically. The apparatus includes a filter, a pump system that pumps solvent through the column. There is an injection mechanisms which we can inject the sample to the column. Columns are packed with different kind of packing materials, polystyrene, styrogel, and other packing material depending on range of molecular weight of that specific polymers. And finally, the injected sample is washed out by solvent and is eluted, and then it's detected. The fractions of different molecular size are detected by different kind of detectors. It can be a UV detector or refractive index detector. It can be a viscosity detector or low angle light scattering detector. And finally, the data is analyzed by a data acquisition system. Here is the chromatogram that are shown here. And basically, this is the output of the retention volumes, basically the detector response versus retention volumes for two detectors. This is the refractive index detector, and this is the low angle light scattering detector, which is more sensitive to higher molecular weight. This again shows two different detectors, a viscometer detector and refractive index detector. And the result can be summarized in terms of various molecular weight averages, number average, weighted average, and the ratio to give a measure of polydispersity for molecular weight distribution. Here is a setup that is used. It's called quasi-elastic laser light scattering, which is used for determination of particle size and surface charge of emulsion polymers, latex particles. Schematically, it looks like this. There is a laser light source that passes through a lens and goes through the sample. And then the scattered light is analyzed by an optical system, which includes a photomultiplier, amplifier, autocorrelator system, and or a spectrum analyzer. So basically, we're looking at the Brownian motion of these particles, which is related to a diffusion coefficient and ultimately to the particle size. This is a setup, capillary electrophoresis setup, which is used to study surface charge of polymeric materials, the latex particles. Here are the results of the laser light scattering system. The exponential decay represents the diffusion process from which we can determine a diffusion coefficient, which eventually relates to particle size. The oscillation is an indication of the net transport, which relates to electrophoretic mobility. Here are the autocorrelation function, basically the output of this quasi-elastic laser light scattering instrument for latex particles with different particle size. The smaller the particle, the faster the decay, the faster the diffusion. So here are these data for 91 nanometer, 176 nanometer, and 481 nanometer in size polystyrene latexes. Again, output data for quasi-elastic laser light scattering, the exponential decay and oscillations. And this is a summary of the result. At the end, we can determine the particle size for different samples, and we can determine electrophoretic mobility, which relates to the potential on the surface of these particles. And finally, these are the references that were used to prepare this presentation. Thank you very much for your attention.